Yes, sir, you are audible.
Yes, sir. You're audible.
Okay, thank you so much.
Good morning, all. I am Karthik Reddy, a research scholar, welcoming you all for the day 4th, session 2 of a NAMPED-sponsored short-time online course on power electronics converters applications in microgrid and vehicular technology from 20th July to 24th July 2022, organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela, Odisha, India. It's an honor and a privilege to me to read the biodata of Professor Avik Bhattacharya, sir. Professor Avik Bhattacharya, sir, is working as an assistant professor since February 2014 in IIT Rourkela. He completed his BTech from Sikkim Manipal Institute of Technology in 2002 and MTech and PhD from IIT Kharagpur in the year 2005 and 2010 respectively. He became student member, and senior member of IEEE in 2006, 2013 and 2018 respectively. Prior to joining IIT Roorkee, he worked for R&D division of Solar Semiconductor, Danfoss Solar Inverter and Samtel Avionics HAL. During his short stay in industry, he filed 2 international patents on the solar pump and power quality. At present, he owns 2 international patents and 1 national patent. He has also published 15 ACI indexed journals and 30 IEEE sponsored conference papers. Among the 15 ACI indexed journals, 9 among them in IEEE and IET. He is also the principal investigator of 3 research projects supported by DST CERP, CSIR, CPRI, and 2 industrial projects supported by companies like Statcon Energia and Tata Power. He has also authored a book titled Introduction to Fax Devices from CRC Press. He has also already guided 2 PhD students and more than 15 MTech students. He has also offered 4 NPTEL video courses and conducted 2 short-term courses in quality improvement program as a principal investigator and a collaborator of GEON courses with foreign faculty. His field of interest are power converter topology, electric vehicles, microgrid, power quality, converters for renewable energy. I welcome you, sir, once again to deliver your talk. Over to you, sir. Thank you.
Thank you. I have shared the PPT. Can you see the PPT?
Yes, sir. It is visible, sir, clearly.
Okay, fine. Go to the full screen mode. It is changing?
Yes, sir. It is moving, sir.
Fair enough. Thank you all the participants for giving me opportunity to talk about one of my area of research. Multi-level inverter has always been close to my heart from my MTech days. So, and new affections actually I have grown for the microgrid application. So when I see that they can be merged, it became a very interesting topic for me. So I hope that I will justify your time which you are going to spend 2 hours with me. Okay. So first of all, we will talk about microgrid first. Then I try to introduce the microgrid in the introduce multi-level inverter and its applications in microgrid. So why microgrid? So as we know that we have a distributed generations. Distributed generation gives the scope of the form of microgrid. So these are the definitions of the microgrid. So and first of all, and others are the why microgrid are getting importance in our present day. The benefits of low carbon footprint, flexibility, reliability, redundancy, and you count on, you can go ahead. So these are the few things that why microgrid matters and why we should study the microgrid, or we should research, we should implement on the microgrid. And unfortunately, that first microgrid came in the Sagardighi in West Bengal. It was a failure. So we should have a detailed case study of what was the cause of the failure of that microgrid. So anyway, so these are the few issues that reliable, flexible, more secure, resilient. So thus we are gradually trying to have a microgrid in our system. Nowadays, most of us, those like you are in NIT Rourkela, I am in NIT Kharagpur. So you stay in a campus that itself can be considered as a microgrid. And many societies are coming out inside the cities that can actually eventually become a microgrid. For this reason, the scope of microgrid is increasing day by day. So these are the few advantages of the microgrid. I am not explaining because I wanted to concentrate more on the subject on the power electronics. So now we require to define few terms that I'll be mentioning frequently. And for this reasons, one is utility grid, and it can be interconnected or it can be disconnected. Once it's connected, we call it the grid connected mode, and once it is disconnected, we call it is islanding mode. And generally, microgrid should have an energy storage. So without energy storage, you cannot have a microgrid. So it should have other renewable energy sources also. Controllable generations, and that is basically that gives you the flexibility, redundancy, and reliability. So there are few issues, like we will integrate definitely the renewable energies, and thus they are intermittent in nature, and they have a source input source fluctuations, and reliability is a challenge according to the environmental conditions. So there will be a challenge to extract maximum power, whatever will be available from this non-controllable generations, because in the thermal power station you can control the governance input to control the output of the control the real power essentially, and that is not possible here. So whatever you will be getting, you try to get the maximum, and sometime once your storage are full and you cannot inject the power, so we require to come out from that mode. We'll discuss a little bit about it also. And load can be controllable. So in India, generally, domestic loads generally pay tariff at a constant rate. So we don't have any motivation to actually control our load. Even if there is a low power generations since some day, so we don't have a motivation, financial motivation to cut short our power generation, power consumptions. But there inside it, so once we have a power cut, yeah, we may form the rule that if you can consume power at a particular peak time, then tariff will be different, and but other case tariff can be the same, and vice versa. And whether you got an electric vehicle in the peak hour, you can use that electric vehicle as an UPS, then you will be given some extra benefit. So those kind of issues can be the welfare society or our institute can implement easily. So these are the flexibility part of the microgrid. Now, definitely there are challenges of the microgrid. Why we don't see microgrid if it has so much potential? One is still a high cost of the distributed generating sources. Only reliable is the solar. Wind requires the structures and etc. Though wind yield is quite more, we can have a micro wind turbines. Maybe actually for the high-rise building especially. So because our houses are meant to be built to sustain 200 km/h of wind speed. So generally we should shut down the wind generations at 20 km/h. So we can, but we have to physically dismantle that structures in case of the high storm or turbulence. Then technical difficulties, that is that we require a microgrid that faces many challenges that will be addressing the subsequent slides. So for this, I am not elaborating here. And thereafter, absence of standard. Like we have a grid code that that formally has a standard, and thus accordingly we require to practice that all the installations, all the new power station, power plant, etc., everything. But we can have an AC microgrid, we can have a hybrid microgrid, we can have a DC microgrid, we can have a different voltage level of the DC microgrid. So these are something and which standard we will adopt. So there are IEEE standards also. So there are we have not formalized that universal standard for the microgrid. Another is administrative and the legal barrier. That's what I said. Like you wanted to motivate consumers' behavior by have a differential tariff. So it is liable to litigation in India because does RWA has a power to do that? So one of the member representatives to this kind of shaping the behavioral pattern. So we may not the microgrid authority may not go for that aspects. A market of monopoly, it is applicable mostly in the countries like USA, where there are few startups, they are working on the market monopoly on the microgrid. But in India, microgrid as a company is still nascent, so or in infancy. So it doesn't have a monopoly here, but we can add that this market still in infancy. So these are, I just told you that we will be talking about the technical challenges of the microgrid. So many technical challenges are associated with the microgrid. Mostly that energy management is one of the issue. So we require to optimize the generations, consumptions, as well as the dispatch or purchase. So this is something that it is not a one-way traffic that we get a connections from the grid or the distributed company, and we are just consumers. So role of the microgrid operator are manifold, and the management of instantaneous active reactive power balancing, that is a power quality issue. So once we are taking power from the grid or we have a power surplus, we can give back power to the grid. In that situations, we should not corrupt or inject a huge amount of reactive power, then we will be penalized for that. And or while taking power also, we should not draw a lot of reactive power. So then also we will be penalized. So for this reason, we say it is PQ control. So there is a technique to inject power. We require to have a PQ control for maintaining the reactive power and the real power balance of the microgrid in mainly the grid connected mode, when you will exchange power in between the microgrid and the grid. And transition from interconnected operation to the islanding is always key. Detecting the islanding is also a challenge, but I am not going into that issues here because that can be a separate topic. And then you require to shift your mode of operation. For the PQ control, you may go for droop control method or VIM method, depending on the kind of microgrid you are operating to. So that require operation, technical challenge, processes, etc., etc. And the fourth, because power system has a huge inertia, like, thanks to the Power Grid Corporation of India, we have a huge inertia, and the maintaining stability of the power quality in the islanding mode is one of the major challenge, because you don't have that inertia, and that inertia is very short-lived, because you have replaced the rotating solutions to the power electronic solution. Essentially, there are fast, slick devices, but essentially it will cut short your inertia. So now let us talk about various types of the microgrid. Now we have a distributed generation. Sorry, pardon me. So we have a non-traditional generations, or in some term we say renewable energy generations. Then that is the electromechanical drives, fuel cell, batteries, flywheel, and then renewable energy devices, photovoltaic cell, wind energy, and the small hydro. If spaces are not a problem, then flywheel is very good solutions. I live in a sugar belt, essentially, in Rourkela. So there is a sugar factory near Mirror, and they had a huge problem of voltage fluctuations. And for this reason, they required to maintain the DG around 30% loading in whole peak hours, that been 5 to 9, something like that. Even though power comes and go, that was also a problem. So and that there's an intermittency, all of a sudden voltage sacks, and then soil problem also there. So I worked as a consultant there. So there we put the flywheel, because the space was not at all a problem there, and ultimately we cut down the cost of the diesel drastically, and flywheel gives a very good solutions of this kind of system, especially in the rural areas or the rural industrial areas where land is not a problem. So we put those flywheels, and ultimately we found that we have cut down the cost of the diesel drastically. Let us come to the few terms that we'll be using very frequently, that is distributed system, distributed DG, actually distributed generation sources, energy storage, and controller and the load. These are the components of the microgrids. Now, of course, as you know, that distributed generations are wind, definitely solar, small hydro, biomass, single phase or three phase induction generator with synchronous generator, even by the IC engine. Generally, we don't consider the last one anyway. But I will talk little here. The topology aspect I will try to cover. That is solar photovoltaic cell that will be integrated to the microgrid. So ultimately, this is the block diagram of the. We generally have in mind that DG means diesel generator. Please consider as a distributed generation, not diesel generator. Primary source, then control and protection, interface media, then we got a point of common coupling. Now, we require to classify the microgrid before I enter into the topologies. That is, the microgrid can be 3 types. I will not talk about DC microgrid here, because we intend to talk about some AC to DC converter, AC to DC or DC to AC converter. So we have a bidirectional converter, but we will talk about the DC microgrid. DC microgrid required to be covered as a separate entity here. So we'll talk about application of the topology in AC microgrid and the hybrid microgrid, where we have the AC-DC combinations. Generally, if it is a greenfield kind of entity, then DC microgrid works better. So it starts from its initial stages. Whereas the AC microgrids, you will find that is an existing one, and you just isolate it and you just put those features which I have described earlier, and it becomes the AC microgrid. And whether the hybrid microgrid, you can, some portion is AC, some portion is DC, because you already have a AC system, you don't want to replace it, and you want also some portion where AC to DC conversion is needed. AC conversion, those kind of multi-stage conversions you want to avoid, and for this reason you make that part DC. Once you do that, then it becomes a hybrid microgrid. So the typical configurations are definitely the static transfer switch, because that is required to an interconnection between the different converters with the bus bar, AC or DC, and also with the grid. Single or the multiple distributed generation and distributed storage unit, and we require to identify what are the critical loads, because let's say leaps are the critical load, so it requires the power backup and few emergency lights in some places. And if it is a hospital, then operation theaters becomes the operation theater are the critical load, etc., etc. And power generation system and the protection devices. These are two issues. Now, this is the pictures of the AC microgrid, but you got a solar panel, you have to convert into DC to AC, and this part you will concentrate more here in our discussions today. And thereafter, AC to AC, we can have of course, we can have a AC DC AC. That is the conventional one for the wind turbine. But we can also convert AC to AC directly by the matrix converter, and then we can actually reduce the requirement of the bulky capacitor, and that can become compact. And I am going to file a patent soon that is around 2 to 5 kilowatt compact product that will give you the grid integration features, and you can directly integrate to the grid of the 110 or 220 volt system. So from there, you just plug and play type of entity will be there, so that you just put on your rooftop, where we have many of us actually in a metropolitan city lives in a skyscrapers, and let's say Bombay, since it is a seashore, and or many places like Vizag, etc., that will be very effective, and you can put those things little height. And for the Kolkata and other places, I found that there is a sufficient amount of the air around above the 30-meter heights, so you can have those entities can be put in. Of course, there is a challenge that once that thermal response comes, we have to physically dismantle the wind turbine. Thereafter, energy storage. I have shown you the batteries mainly. It can for the different kind of storage. If you want that fluctuation to be terminated, then we can go for the ultra capacitors. And whereas you want to store some energy in hours, then generally battery, and if you don't have a problem with the space, then even 5 will. And thereafter, definitely the AC to DC kind of load, then we got a very LEDs and etc. Please understand these are essentially most of the lighting load are essentially the AC DC load nowadays. And now we got a AC load also. We got a fans etc. that can also be used here. Now, of course, just talk about the power electronics in the microgrid, where you will convert what is the role of the power electronics here, because these sources, wind or solar, has got intermittency. So due to that, we require to it will be a fluctuating kind of load, fluctuating kind of source, sorry, and we require to collect the maximum power, provided that grid is connected or storage is not full. If that two condition was not satisfied, then we have to change the mode. So for this reason, power electronics role is to essentially harvest the maximum power from the renewable energies and throw it to the grid, storage, and feed the critical and the non-critical load. Once grid is off, then try to feed both critical and the non-critical load. But SOC of the battery or anything, if the storage goes low after some time, then you can think about to cut down the non-essential load and feed only the critical load. So in that way, it will operate, and there is a huge role of the power electronics to play. Now, we generally combine since there is a intermittency and there is a problem of reliability, we combine the renewable energy and the storage, and we integrate them and use the term called energy resources. So renewable energy with the storage, it is your resource. So that is something that smoothen out the effect of the intermittency. So for this reasons, the power electronics are widely used for this renewable energy and the storage. So what are the tasks of it? Definitely the giving the stable and the reliable power supply to the consumers. And if you have a surplus, then you can feed to the grid. If you have a deficient, you can take the power from the grid at high quality. So next part is high performance operation. It deals with the good power quality and high efficiency and regulation of the active reactive power and secure communications. So that is something very important, because this power converter required to talk with each other to change the mode and etc. Now, this is a hybrid microgrid where some portion is AC and some portion is DC. We have a AC bus and DC bus, and in between we have a bidirectional AC to DC converter. So, so for this reason, there will be an interchange between DC and AC load. So generally, this AC load are catered to the AC part, and DC load catered to the DC part. So for this reasons, wind farm, you can have a DC to DC converter with the boost would require a rectifier essentially. So solar is DC to DC, we can have a unidirectional, and battery we have not marked it, it is a bidirectional, please note that. And DC load is unidirectional, provided that it doesn't have a DC motor kind of thing, which can have a regenerative braking. So similarly for the AC loads. Now, these are distributed resources, wind energy, solar, fuel cells, and then the battery storage. Here, ultra capacitor has been shown. It can be battery also. Then we got a AC to DC, then DC to DC, then again DC to DC. And ultra capacitor, since has a very fast response time, we require, and it is a bidirectional. For this, it is marked in pink, and same way for the transformer. Now, the role of the power electronics in the distributed energy. I just told you that I shall elaborate mostly on the renewable energies part. So this is a distributed energy. It can be wind, PV, micro turbine, or it can be from the storage like battery, flywheel, etc. So we have a AC to DC or DC to DC converter. Then we have a DC to AC converter. We can use direct matrix converter for direct AC to AC converter that I am not showing here. Output of the interface module, generally we require the filters to filter it out, and then we got a point of common coupling, we got a local load, then utility, etc. Now, these are the points, for DC output like PV, fuel cell, batteries. Typically, they need to change the voltage level. So we require a DC to DC converter. Whereas DC to AC inverter module is more generic, and the module and converts DC source to the grid compatible voltage, or if you are integrating the 3-phase, then 400 volt line. If it is a single phase, then 220 volt RMS in India, etc. The output voltage module and the filters we require a filter in between, because we have a high frequency switching, and that will generate sufficient amount of the high frequency element, and that required to be suppressed first. And thus what happened is the output from the inverter and the monitoring and the control module operate with the interface and containing the distributed energy and the utility at the point of common coupling. Then power electronics interface also contains monitoring and the control functionality, and thereafter another issue is that monitoring function typically includes real power, reactive power, which generally you should inject the good power quality, and voltage monitoring, there should not be sags and swirls, and at the point of the distributed resources of the utility. Now, after that, why it is employed? It is for the active filtering, because if you have a nonlinear load connected anywhere, then it can absorb the harmonic part into it, and if you have a not only restricted to the now active power filter, not only restricted to the compensation of the harmonic, it can compensate the reactive power as well as it can give us the balanced power. So unbalanced, that negative sequence component also can be suppressed. So for this reason, this dual active converter, AC to DC converter, DC to AC or AC to DC converter, can play that role of the active filtering. The function of the power electronics compensator is this, definitely, which has been written down. So increase the power transfer capability of the line. It is done in the mostly in case of the fax devices, that is in a transmission level. So we generally call nowadays it is the DFAX, that is distributed fax. You can bring down the concept of the fax, that is flexible AC transmission system, into the level of the distributions, and there instead of the generally we use UPFC, Unified Power Flow Conditioner, and here we use UPQC, Unified Power Quality Conditioner. Mostly its task is to maintain the power quality, and also it can control the power flow. and enhance stability, and that's what I said initially, that improve power quality. So we have a multiple objective for the power electronics converter. One is control of the grid voltage. Definitely, if you have a voltage sacks and so on, those power electronics devices integrated with the energy storage can inject the real power, and also, it can inject the voltage perpendicular to the current. Then it doesn't require any real power, but then the compensations require to be more, because because you are integrating, let's say voltage has sack 5 unit, assume that 5 unit the voltage you require, and it has been sacked by 20%, it has become the 4 unit. However, you require to inject the 3 unit of power to compensate that voltage, because you are trying to compensate in quadrature. Whereas if you can inject in phase, you just require to inject 1 unit. Okay, so that is the advantage of having a storage into the system that enables you to this power electronics converter to inject a voltage in a phase component, and thus you can mitigate the sacks and soil very easily. Whereas if you don't integrate those power electronics with the storage, then we require to manipulate the voltage that will be only managed by the reactive power. So you will find that rating of the devices will be more. That I'll come little later. Anyway, so that is the control of the grid, and then control of the current, because generally we'll see that all those grid connected converter essentially will be operated voltage. It is essentially a VSI, that is voltage source inverter, operating in the current control mode, and it will also control if the grid is stripped, then it will maintain the DC link, and then the control of the AC voltage and current, that also can be done, and control of the harmonics, etc. This can also be done by this power electronics, and the speed control and so on. These are essentially for the wind MPPT tracking. So we will adjust the pitch angle accordingly so that we can harvest the maximum power at a particular wind speed. That is a mechanical aspect of it. And so command will go that it is not at the particular orientation of the wind. Maybe those pitch angle can be controlled so that power can be increased also mechanically. And so once it is done, so speed can also vary. So that will lead to the MPPT point. So that can be a closed tracking with the mechanical system. So that also will be done with the MPPT. Now, I am giving you an example of the 2-level inverter. So you can see that how a grid connected operation performs for the active rectifier. So assume that it is a 3-way system. So there AC to DC conversion or DC to AC conversion also can be taking place. So you will sense this currents, and from this current you will have a voltage loop. So you will essentially see that current will be multiplied because you sense this current, and that current will be essentially multiplied with the voltage, and will synthesize a resistance. So that resistance will say that it is an artificial resistance, equivalent resistance. So accordingly, the reference will be sent voltage to the current, and then that will be compared with the V0, and we will have a voltage loop, and we will operate also the inner current loop that will not allow to cross the current limit. Essentially, it gives inherently the current overcurrent protections. So both have been simultaneously implemented. For this kind of PWM rectifier, we say it is a voltage control. Now, let's see that where it finds its applications. So it will find its applications can be in a solar inverter also. Okay, but there we will be dispatching mostly the power to the grid. So PV converter can have a dual stage. This is essentially the DC to DC. Then we can have DC to AC. It can be integrated together. That is called dual stage. Or you can have a single stage inverter, that is DC to AC. DC to DC converter is required to track the MPPT points and to maintain the DC bus voltage. And then once you maintain the DC bus voltage, then it can be easier for this inverter to inject power, and thus you can play with the modulation index. Whereas in a single phase, where you have a dual task, you will this AC to DC DC to AC converter not only inject to the load or the grid, but also essentially try to track the MPPT. That require a different kind of topology altogether. So that will be discussed in later. So first one, that is the dual stage conversion, has been shown here. So first we have a PV. Since there is a switching, we require a small filter in input. So we can allow to pass the current through the filters. Otherwise, the PV panel will conduct because there will be a capaciting effect and current will flow to the ground. Then we have a DC to DC converter. So that will track the MPPT and maintain the desired DC level voltage. And thereafter we have components. These are essentially DC to AC converter, that is basically the major inverter that we will talk in details. And we have our filters, then you will integrate it to the grid. Now, of course, the grid connected solar inverter, we found plenty, and this slide doesn't require much explanations. So we just give some data so that we can see that this is the PV market demands. It has been taken from MNRE's website. It is the data till 2017. Of course, there is a faster improvement, but due to the COVID, the last 2 years, the development was slow. Now, let us come to the grid connected solar inverter. That is something that our area of interest in great detail. There are various type of grid connected inverter, so we can use as a self-commutative. That was the early type of inverter. So we used to use the thyristors in a DC link, and it is operated in a full control mode. So we used to change the firing angle, and in that way we used to operate as an inverter. So that is the self-commutative inverter. Then we have a line commutative inverter, and which has been phased out. Now, self-commutative inverter are the two kinds. One is that voltage source inverter I talked about, and it can be current control mode or the voltage control mode. CSI we don't prefer because it requires a huge value of the inductor, and that huge value of the inductor itself is a great demerit considering the cost and the bulkiness of the system. Now, of course, these are the basic difference of the VSI and the CSI. The input of the VSI is a voltage, whereas the CSI is a current. CSI we find in application in the high power drives. VSI we generally prefer here because of the compactness, the flexibility, etc., etc. Now we shall categorize a different kind of solar inverter. Solar inverter generally of the three kind, centralized. So whole solar plant generally is scattered by the single unit, that is called centralized inverter. Then it made of strings. Strings essentially have a different battery, and string level battery string is preferred because string will have a particular number of strings will be connected in series and parallel and gives us the particular power rating input. Then you can have a multi-string, so many strings can be integrated, and thereafter we got a AC module. So one panel will come with the integrated MPPT tracking, etc. You can plug and play the devices, and that will be integrated, and that gives us the voltage. It is just like a voltage bricks. This is an example of the first one is a centralized technology. So we'll connect, we have a diode to block the reverse flow of power. So we got this power to be given to the DC to DC converter. So here MPPT tracking is composite. So for this reason, the partial shading and etc. cannot be addressed very well. So we can optimize the tracking at a particular point. Then we have a three-phase connections. Then it is the DC to AC conversion can take place. Okay. Then the string technology. So we integrate the strings, single strings with a particular voltage that fits the. So we require to track the MPPT, the DC to DC converter, and then we have a inverter. And thereafter, we can have a multi-strings. Multi-strings, it is just like series parallel combination of the strings and gives you the particular voltage level or the power level we require, and that connected to the grid. Otherwise, last one is the AC module. That's what I talk about. Only one company in USA makes it. That company name is Enphase. So there we can integrate the DC to AC directly. Here MPPT tracking is better, even though cost of the power electricity is more. But this company claims that, so since the cost of the energy will go high, we should see that more and more power input compared to the other inverters. So energy yield can be compensate the high capital cost within a particular payout time. Provided that, now we have a high mod, please understand that, even though at USA right now we have a huge inflations, but in a pre-COVID sessions, inflations and the mortgage rates was low in USA. So the cost of money was low, whereas the cost of the energy was high, and thus this model worked. So I am not very much sure that the high mortgage rate that he was having, how this model is sustained. So centralized, it is the low cost due to the central inverter. Cost of the capital cost is minimum, whereas disadvantage are many. The DC losses are high because you require to have a big DC cable. Since you have one single inverter, we require to fetch maybe 2-3 kilometers. So power loss due to the centralized we require to track the MPPT, and MPPT cannot be tracked because of the partial shading condition and different environmental effect in the different positions. And in case of the failure of the inverter, total power will shut down. So there is no reliability, less reliability, and no redundancy. And cost is low compared to the string inverter, and it generally comes in the power rating of the 30 to 50 megawatt. This is the string inverter. So reduction in the loss can be minimized compared to the string, compared to the centralized inverter. And losses in the string diodes are also can be eliminated, because please understand that these are the power diodes generally will have a epitaxial minus n layer, and for this reason power drop of this diode is not 0.7 volt. You will find those diodes are quite high, up to 1 volt or 1.2 volt. And if 100 amperes current is flowing, please see that what amount of power, because around 100 watt or 200 watts power loss is across the diodes. So you require to provide the heatsink for that. And it is just electric bulb, so of 100 watt. So that is something not accepted. So then the safety against the failure, then good reliability and the flexibility in the design is also possible. You can essentially put the number of strings what you require, etc., etc. Used for the low power rating, most of the rooftop systems are the strings inverters, and it is a high cost compared to the central inverter. And generally, if it is single phase, it comes up to 5 kilowatt, and if it is 3 phase, it can go around 20 kilowatt. So multi-string essentially a 3-level 3-phase inverter, and reduction in the number of losses. So losses of the string diodes are eliminated. MPPT tracking is better because every string will have a own MPPT, and the voltage amplification is always better because every string is supported by own booster, one DC to DC converter. Let's not put that topology. But a disadvantage are strings are connected in a single inverter. Thus definitely reliability is a question mark, and additional losses due to the multiple DC to DC converter. And cost is definitely higher, and it is generally 3-phase, and it can go up to 50 kilowatt, and also I have seen 100 kilowatt for the ABB solar inverter. So AC module, there are many advantages, because appropriate for the residential purposes, it is a kind of plug and play device. No mismatch losses between the module, because this internal resistance is this, or solar radiation particular panel is different. That doesn't matter. Easy to failure detection, because ultimately it gives you the voltage. If it doesn't give you the voltage, that means it is not working. And flexible, expandable, good for mass productions. You just integrate like in a flooring, and it has an average life period, the company claims, is 25 years. But cost is quite high compared to the other system. It comes with the generally 500 watt to 600 watt. Now, so these are the mainly the topologies available. So we shall see that how does it work. So generally the grid connected solar inverter, that is the abbreviation of the GCPV inverter topology, are generally classified into the number of the processing stage, power decoupling, and the transformer and type of interconnections. So number of processing stage can be single stage inverter, multiple stage inverter, and multi-stage for the multi-string inverter. Let us see that one by one. So one is the PV, then this is simplest. DC to AC, then grid. It can be your micro inverter, which I have talked about. And mostly the micro inverter will have these configurations. So then you got a second one. So you got a boost converter. Generally, it is DC to DC converter. It will change the level of the this input voltage of the system, and it will track the MPPT. Then it will feed to the again DC to AC converter, that is an inverter, and then it will be connected to the grid. And you see that it is a multi-string. So another PV panel will be there. So DC to DC converter will be there. It will track its own MPPT and maintain the same voltage. Then it will be integrated to the inverter. Now the power decoupling is required to filter out the voltage spikes to pass through only the DC component of the source voltage, and it is generally accomplished by the large electrolytic capacitors, and it is quite vulnerable. For this reason, the panel generally comes with the warranty of the 25 years. But problem lies, most of the panel companies' life is less than 25 years. Anyway, that leave apart those issues. So, so what happened? But solar inverter, you will not find that much of it is living because of the electrolytic capacitor. Electrolytic capacitor only has a lifespan of 5 to 6 years, but they increase the reliability a little bit. It comes out to be maximum 10 years, whereas the switches can go up to 10 to 12 years. Then there is another type of grid converter. So that is the transformer interconnections. Generally, it is specified in the grid code when you are injecting power to the grid, whether you require a transformer or not. And in general, we require the transformer. Few countries doesn't require it. So that transformer can be line frequency, and that can be a bulky one, whereas it can be high frequency, it can be slick, and that is the modern technology. So I just give you the example of first one, that is the power frequency that is connected in between. So it requires a bulky transformer, and thus, since it is operating at 50 Hertz, thus it is costly as well as a bulky. Whereas, the second one uses a full bridge converter in between, and it is high frequency transformer. And for this reason, you don't require any further isolation in the grid side. And since switching frequency can be 20 kilohertz instead of the 50 hertz, so accordingly the size will come down. And so this is the C. So there's a little difference between B and C. Here essentially you got AC to DC. DC to AC. Then you have a high frequency transformer. Then output is AC. Then it is get rectified by the control rectifier or synchronous rectifier. Then essentially you get here DC. So this is for the DC microgrid, and it is for the AC microgrid. And so transformer-less topology, sometimes it has been preferred. So this one, lower one, has been shown as a transformer-less topology, because transformer-less topology will have a higher efficiency and cheaper than the inverter with the transformer, because you are saving the cost of the iron and the copper. And extra care should be taken then the solve of because Once you got a transformer, it helps you to gives you the galvanic isolations, spike suppressions, and many others, ground current suppressions, because all those nasty elements can be absorbed by this transformer. When we try to remove that transformer, then we require to have a extra cautious about those issues. So extra care should be taken to solve the DC current injection problem, because if there is a DC biasing, ultimately we are going to inject the DC power into the system with the AC power, and it may saturate the grid side transformer, and we will be penalized for that. No galvanic isolation, that is one of the problems. If surge comes, etc., it may damage the whole system, and electrically hazardous because it gives us the isolation, especially the detecting the islanding mode is a problem. So these are the more issues. And voltage fluctuation generated EMI should be around the PV array. So we have to find it out the method to suppress the high frequency conducted emissions and the radiated emission. And for this, you can see that we have accommodated. This one is essentially the common mode choke, and then we have a capacitor of CDM, this two. So we generally say that it is a common mode noise suppressions. So, and we have a two kind of suppressions. This is essentially for the common mode, and this is for the differential mode. So we require to calculate those capacitors for the common mode capacitors and the differential mode capacitor to suppress the noise. Otherwise, noise will be high. Okay. Now, as I told you that there's a different kind of topology possible in the grid connected inverter. So there's a transformer less topology, as I have seen the previous slide. And of course, we can go for the multi-level inverter. We know that multi-level inverter has several advantages over the two-level inverter, because advantages are we can name 5, 7, 8, 10, any numbers, and we are living on the multi-level inverter because it gives close, the staircase waveform will be the close proximity of the sine wave, and thus the switches has a less DVDT, rate of change of voltage. So stress across the switch has been reduced, and we know that an instantaneous error between the sine wave and the injected inverter wave of the pole voltage has drastically reduced, because we require maybe the 30 volt. So if your two-level voltage is switched on, it gives us a 300 volt, because let us consider that at that point we require the only 30 volt. So that is one of the error. And also, if it is a two-level inverter, it can gives you the minus 300 volt when you require the. It is possible when you are operating in a bipolar PWM technique. So, and thus it gives to the huge common mode conductions in between the pole of the inverter to the the mid. So if it is touch connected load, the load neutral point to the midpoint of the capacitor. So there are many advantages of the multi-level inverter, and for this reason we prefer the multi-level inverter. Then next is essentially the Z source topology. So we can have Z, zeta. There are multiple Greek alphabets that has been available with the solar inverter topologies, and essentially task is to boost the voltages from the solar panel. But since it comes with less number of switches, it has its own merits and demerits that we will be discussing in a subsequent time. And then next, essentially, is the soft switching inverter, because till now the best efficiency solar panels are the monocrystalline solar panels. It has an efficiency close to 17 to 18%. But if we unfortunately operate an inverter that is hard switch around 85%, so, and we spend $1 million to increase the efficiency of the solar panel from 17% to 18%. So that spending is not justified. And till now, the solar panel is the most costly part in the bill of material or the balance of the system of the solar integration. For this reason, the soft switching inverter is preferred to increase the efficiency, and we know we have a voltage source, zero current switching or the zero voltage switching. Either of it can be taken based on the topological requirement we called there as the resonant inverter. Now, transformer-less topology, there is another issue. The degradation of the PV panel required to be reduced, because since there is no isolations, ultimately the solar panels will hold some voltage essentially, and the ground will be at zero potentials. So when switching occurs, so earth current will flow in between the solar panel to the ground, and that required to be prevented, mind it. And if we don't do that, then we will find the degradations of the solar panel. So, and they mentioned that earth current to be restricted in an installation. So, based on that, it is possible to subdivide the single stage grid connected transformer-less inverter as sinusoidal pole voltage, constant pole voltage, and grounded pole voltage. We'll see subsequently what are those. Now, the first one, that is SPV, has been preferred by the manufacturer for a couple of reasons. For high efficiency, DC output voltage higher than the grid voltage in magnitude, and so that you can inject power. And most of the PV panel currently installed and built with the traditional silicon technology. That is also the issues. And drawback of the two other classes with respect to PVs are CPP inverter require double stage DC to DC output voltage if you don't have a sinusoidal voltage. And the last one, that is the grounded inverter, presents the lower conversion efficiency because high voltage and the high current stress across the power switches. So I just show you one grid connected solar inverter. So this is the essentially you can count its level, So I just leave it to you. So this is the high efficiency transformer-less topology. This is the switch, and it is the G1 and G3. G1 is a gate of S1. So accordingly, you can see these are the G1 and G3. And in between, you have S2 and S4, that is essentially G3 and G4. And whereas, you can see that G5, is S5 when it is triggered. So then how it will do, and G6. These are the two entities will ensure the ground voltage. So it is essentially a two level, but in between there is a ground pole voltage that will gives you the more flexibility, that is the SPV, and this has been preferred. Now we shall talk about the multi-level inverter, because I have talked a little bit of the multi-level inverter. So that is something we should talk about it. And the better quality of the waveform in terms of the THD, because it becomes more staircase. So one staircase, number of stair increases, it can be approximated to the sine wave, and thus better harmonic profile, and it will reduce the requirement of the bulky filters, lower DVD ratio, more degree of freedom and redundancy. Mostly it happens with the flying capacitor, and possibility of the modulation with the low and the high switching frequencies. That is also one of the advantage, because sometimes we have a asymmetrical cascading H bridge. So some switches may be MOSFET, some switches may be different entity, maybe GTO or IGBT. So the first switch, as we know that first switching devices cannot handle more power. So more power will be handled by the low frequency devices, and whereas the high frequency devices can be operated in between to make the staircase smooth. So voltage rating of the power switches are much lesser. We know that the power rating generally exponentially increases with the voltage rating as well as the power rating. And availability of the multiple redundant states, that is also an advantage. Fault tolerant operation is possible. Equal load sharing among the different devices, thus you will find that heating is uniform. So renewable energy source can be easily integrated with it. So these are the few advantages based on the waveform and the topology. So multi-level inverters are definitely the power semiconductors, and the capacitor voltage source that when properly connected, it can generate multi-stage test of the output voltage. Now this is the realizations of the multi-level inverter with the help of the single throw multiple switches. Single throw multiple switches. So first one is a single throw double throw switches. So it can be connected to the plus or minus DC bus voltage. Thus it is a 2-level. And second one is a 3-level. It can be connected to the plus or minus. So we can see that, at this point, we are injecting the minus VDC, but we require, the positive voltage. So there is an huge instantaneous error in between the actual voltage and the pole voltage. Whereas it has been subsequently reduced, and since we had a 0 stage, so in between this neutral point and the neutral point of the load, so there will not be any current flow. So that can be drastically minimize the requirement of the common mode noise. So then it is a multi-throw switches, single pole multi-throw switches. So it gives us a staircase waveform, and that can be a closed approximations of the multi-level inverter. And this is the classifications of the multi-level inverter. So we got a DC to AC converter. So this is a single source. Then we have a voltage source, current source inverter. We have not talked about, but of course it is possible. And line commutated inverter also with the thyristors. Then we have a voltage source, multi-level inverter, and the 2-level inverter. Multi-level inverter can be further classified to the multiple DC source. So that is quite familiar in case of the solar panel. because multiple DC source can be the multiple strings of the solar panel, and the single string storage, cascade H bridge, flying capacitor is the single stage. Cascade capacitor H bridge is a multi DC source, whereas the single DC source are the flying capacitor and the neutral point clamped, and these are unequal DC source and can be equal DC source. So we will see that what is the advantage of this cascade H bridge in detail for the solar configuration. Now, as we know that this is the typical NPC we call tight clamp multi-level inverter, and next one is the flying capacitor. I'll show a little later, and then cascade H bridge. NPC, you can, that's what I was talking about, a 3 level, this point and this point, capital N and small n. These 2 point voltage is meant to be 0, so there is no power flow in between these 2 points, and current flow in between these 2 points. And we know that how does it operate. First, if you want to generate the S1 DC bus voltage, positive DC bus voltage, then we require to trigger S1 and S2. And then if you want to generate the next one, that is minus DC bus voltage, generally we don't do that. So we require to generate, trigger this complementary switches at the lower leg. And generally when we want to trigger, generate the 0 voltage, so both these switches S2 and SA2 and SA1 bar is been triggered, and ultimately it depends on the which voltage is more, pole voltage is more, or the capital and midpoint of the capacitor is more. Accordingly, the current gets a path to flow. If that in general the negative negative part of the sine wave, this load voltage is pole voltage of the inverter is negative, then we find that capital N is more voltage, is a positive voltage compared to the inverter pole voltage. Then path will be through the diode and SAS2, and it also gives an advantage because previously the switches conducting was SA1 2, so it also gives the allow the negative current flow capability of this load. So this is a flying capacitor. So it will have a logics. So you can see that upper switch and the lower switch are complementary, and middle two switches complementary. So if SA1 and SA2 are turned on, the lower two switches are definitely on. And here, once the midpoint is generated by a little bit of different means, so SA1 is triggered. Please understand that essentially the SA2 will be off automatically, and you can give trigger to SA2, and thus you can give trigger to SA2 bar. So the current will flow with the VDC and half of the voltage will be applied. So flying capacitor gives us the more redundancy than the NPC, but we require to be actively charge and discharge the flying capacitor. That is a very big challenge. Now let's come to the multi-level inverter. One of the problem of this two topology is that huge component count. Please note that number of diode in case of the NPC increases exponentially. It is n into n minus 1. Generally, we prefer the odd number of level because in between we have a 0 voltage level. Okay, we don't prefer 4th level or 8th level. We prefer 5th level or 9th level. So 0 voltage has always advantage to suppress the common voltage. So for this reason, if we have a 9 level NPC, then we require, 72 number of diodes. So whereas, in the flying capacitors, it is n into n minus 1 by 2, we require, 36 number of capacitors. So the component counts drastically increases in these components. So now let's talk about the CHB, it is cascade H-bridge multi-level converter. One of the advantages for the renewable energy perspective is that getting a multiple DC source is not a challenge. Solar panel can itself work for it. Solar panel or strings. So thus you have what we require to produce by the transformer isolations. So that is no longer required. The single phase H-bridge converter is able to generate this different voltage level. Each leg has only 2 possible switching states, and to avoid the DC-link short circuits, and zero level can generate the by the opposite phase triggering. So this is the this is an applications of it. So once we trigger S1 and S4, just like a 2-level inverter, we get the positive DC bus voltage, and 0 voltage can be triggered either of triggering the lower 2 switches and the lower 2 or upper 2 switches, since it depends on which you prefer, and we don't want to short a leg, so accordingly we require to trigger it, and then we should change over to the minus voltages, then S2 and S4 have been triggered. Now, having said that, let us go to the applications part of the PWM rectifier. I have shown the 2-level. I shall design it for the 2-level. So then we shall switch over to the 3-level. So task of the active rectifier to take power at unity power factor with good power quality. So for this reason, the DC output voltage required to be regulated and input power factor required to be close to the unity. The converter consisting of 3-phase bridge, high capacitance on the DC side, and 3-phase inductor in line side. So, these are the phases, we see that, Vs is the source voltage, where Vf is the inductor voltage. We see that there is an inductor in between. Okay, so for this reasons that comes into the pictures, and so you can inject the current in phase, and for this the voltage required to be little out of phase lagging, so that the voltage and current are in the same phase. Then you are taking power, into the system. And also, there's a different mode of operations. Like A is a unity power factor operation, so Vs and Is are at the same phase, whereas in B you can see this one essentially it is lagging, so current you taking as a lagging power factor. We don't do that anyway. Sometime we go for the leading power factor, then Vf required to be more, your DC bus voltage level required to be more. So that is something we require to correct the correction of the power factor in grid side, and we can also keep back the power from the DC side to the AC side once it is integrated with the solar or any other sources or storage. So then then the current will be 180° out of phase. Then according to the convention, we are sending back to the power to the grid. Now, of course, these are the 3 voltages, and then V1, V2, V3. Then we require to convert them into the alpha beta frame. Alpha beta frame is a stationary frame. It means that just the coordinate transformation what we did in case of the for the three vectors. So from 3 vectors to the xy coordinate, it is something like that. So once we receive that, so then we shall go back to the rotating reference frame where we want that alpha beta phase, alpha beta these voltages will rotate with a synchronous reference frame with an angle omega. So these are the expressions of the VQ and VD, and thus we get the voltages in the stationary rotational frame of reference. Once we get a rotational frame of reference, our convention is that we are rotating with the omega. So many quantity looks like DC, and thus our it is called SRF, synchronously rotating frame, or vector control, popularly known in case of the drive applications. Same concept has been derived here. So these are the once we write it down the equations. So there will be the cross term, mind it. So with VD there will be a VQ, ISQ, and then with the VQ there will be IST. So this will be the expressions of the VD and the VQ, and we can write in the matrix form also, on the short form also. And where R is the inherited resistance present into the system, and LS is the that active power filters inductance, and others are known parameter to you. And please understand that power dispatch, we say it is between point A to point B. It is V1 into V2 by X into sine delta. This application holds good when X by R ratio is quite high. But in case of the microgrid, R is not negligible because there's a switching losses, etc., etc. All are resistive in natures, and inductors comes with the sufficient amount of the resistance. So for this, it all adds up. So thus, X by R ratio in general we consider it is more than 0.7 in case of the transmission side, but in a microgrid it can be 2 or 3, and we will find that more the less this ratio, power transformation becomes more difficult. So control has to take care of those issues. So this is the block diagram of the power controller. So essentially your right hand side there is a grid. So voltage controller will take care of all this output and calculate this. From there it will calculate the ID star and the IQ star that required to be injected or take out from the grid. So current controller, it will sense the current and will convert to the ABC to the DQ frame, and then that current reference will be given the triggering so that it can inject the desired current, and the voltage has to be maintained accordingly into the terminal of the inverter. So suppose there's a fourth point, it is quite important, that the reference of ith distributed generations is rotating at a frequency of omega I. The reference frame of one is considered as a reference frame with the rotating frame is the WCOM. So we require to match all this reference frame together, then only it will look like this. Now the angle of the ith distributed generation frame with respect to the common reference frame is denoted by the delta I, and that satisfies the following logic. So control block, that is the issue of the droop control of the frequency. So that's what we use the droop control. The power controller block maintains the droop technique and provides the voltage reference V0 into Di and Vq into Qi for the voltage controller, as well as the operating frequency omega I for the inverter bridge. So it will operate in that differential mode. So this is the VOI and IOI. From there it will calculate. This is essentially the power. Okay, so this power will pass through the low pass filter. So all the harmonic content will go out. So this is PI, and essentially the cross term, if you multiply, we get the reactive power. So this part is that P VD into VDID plus VQIQ, whereas VDID minus VDIQ, it gives us the reactive power, so it will pass through it. So essentially you get QI. From there, you will have a I reference, and the PI controller will ensure this matches with the omega I gradually. And same way, so this is essentially related to the something like the excitations of the alternator. So essentially from there, it will take the input of this E. That is so then from there the voltage will be calculated. So the differential equation of the power can be written in that way. So you just differentiate it, P and Q, and thus this block diagram of the power controller, essentially you will find that the VOI star, the output voltage, will be E minus PQ into IQ, and whereas this we require to set it 0 for the unity power factor operation. So that is the way we will design controller, grid connected converter for integration for dispatching of the sending power. And this is some applications of the block diagram of the voltage controller. You have the output voltage, and this is a reference in the V frame because VQ, you know, it is 0. So essentially it is the actuals one, then you keep KP and KI, then you multiply with the omega into CM into Fi, and that gives you the current reference for the ID. Similarly, you can calculate the IQ. So differential algebra, the vector controller, we can jot it down essentially. So VDO I into A will be DI, and this will be the reference. Sorry, this will be the reference for this D-axis current, and this will be the reference for the I-axis current. How you design the KP and KI are the biggest designing challenge for maintaining the power quality of it. And this mode of operation is essentially the grid connected mode. We call it as a PQ control. So what I refer as a PQ control, you maintain the PQ control in this way. So once you get the current reference, we require to track the current reference. So that is called the average current mode control. And thus the actual ID and the reference ID is being compared, fed to the PI controller. So that error, that output of the PI controller is multiplied with the XL. So get the voltage with the Q axis current. Please see the reference, then only you will understand. And so then you get the voltage reference from the VQ. Similarly, from the IQ, you calculate the current reference. Current reference you have calculated, so it has to be separate from the actuals one, and then multiply with the I into XL, and thus you get the voltage reference from the VQ for the inverter, and that you require to convert again into the DQ frame to the ABC frame, and or the space vector modulation, whatever you want. So from there, you can convert it to alpha beta frame also if you go for the space vector modulation. And if you're using the multi-level inverter, you can go for the multi-carrier approach. There's a many way to do that. So from there, essentially 12 and 13 gives us the voltage and the voltage reference for the PWM. So in that way, we are going to control the grid integrated controller in case of the microgrid. So the current control source inverter contains an inverter, and definitely it is connected to the DC side with the help of the maybe the solar panel fitted with the DC to DC converter, and that can be considered as a power source. And the current controller adjusted the direct and the quadrature axis current is IOI, and alpha I calculators used for the loop control method. And there's a many other method. Anyway, I am not considering it. So this part is the current control block diagram, and this part is the calculations of the alpha I. So from there we can calculate the alpha. Now we have done these calculations for the VD and VQ, and this is the, now we are going for the current mode control. Now previously, what we did, it's a voltage mode control. So voltage mode control has a problem, it doesn't give the direct control over the current. So over current control is also we require a separate entity. Whereas in the current control mode, that is not required, but to implement the current control mode, we require an extra controller. So essentially, we know that for the unity power factor operation, VQ will be 0. So for this reason, it is compared to the VQ, and we put it to the PI controller, and we get the value of alpha I. So that is something like, it is called PLL, okay, the phase lock loop. And ultimately from there you will get the VD. So that alpha I is required in this case, and coordinate transformations is sorry. So for this reason, this part is the same of the current controller. So you got a reference current and the actual current, and you have calculated this current mode controller. So where this lambda del I and lambda qi are the auxiliary state variable defined by the PI controller, and IODI and IQDI are the direct and the quadrature component of the output current in the block diagram of the DG. And thus, if you know this methods, so this expressions, from there we can go for the current mode control. So what we can conclude here for direct access mode control for the PQ methods, we should go for the multi-level inverter topologies, even though it has some limitations, and increasing the level definitely require the more number of switches, but each switch require to be combined with the gate driver unit and the heatsink, and thus maybe the overall solution may be little bulky, but as far as the reliability and the efficiency is considered, then there is a more motivations is going for the multi-level inverter. And these are my references. I wanted to finish right now. If you have any question, please ask. I'll be happy to answer the questions. because I want a question answer sessions.
Participants can ask the questions to the speaker.
Good afternoon, sir. Yeah,
Yes,
myself
please.
Shashank. What is the technology readiness level in multi-level topologies in our country, sir?
Our technology doesn't depend on the country. First of all, it depends on the what kind of system you're talking about. Let us show you the slides and let me try to explain it.
That is MPC, sir.
Sorry, please repeat the question.
Multi-level power converters. What is the technology readiness level in India?
No, readiness level is there. So because multi-level inverter was reported by Akagi in 1984. So it is not very new technology. It is a proven technology. In solar inverter, as far as solar inverter is concerned, unfortunately, most of the solar inverter companies, those who are Indian manufacturers, they use the two-level inverter. But if you see the solar inverter of any foreign companies like ABB or the SMA, they are all multi-level inverters because multi-level inverters has a lot of advantages, and for this reasons we are and now so far my knowledge goes, most of the central inverter are multi-level inverters, also for the Indian manufacturer.
Oh, okay, sir.
Any other questions?
Good afternoon, sir.
Yes, please.
Sir, my name is Mohan Krishna. May I know the new advancement in multi-level inverter, sir?
Plenty. Especially the solar. Okay. Please see the work of Professor Sumit Chatterjee and Chandan Chakraborty. So you can see that there's a topology called PECAMVT cell. It is just a derivation for the simple for the multi-level inverter. Nowadays, with a PECAMVT cell, with a cross-connected sources, with a very less number of switches, we can get 13 level, 21 level, any this kind of levels. And since those strings or the panels can be the sources, okay, isolated sources. That is one of the advantages of the solar panel. So you can have a multiple level very easily, and that cuts short the requirement of the filters drastically. If you have a 13 level, you see that component count for your NPCs or the flying capacitors. Okay. And also CHP has this advantage. CHP with the different kind of voltage in a DC link, of course 3 CHP you can say, sir, I can go up to 7 level, fine. But my student has already submitted a paper in a review stage. We went to the 87 level. Okay.
Sir,
yes, please.
Maximum, how many levels we can go for, sir? Maximum advancement, so that It can improve the quality.
That depends on the requirements. Okay. So, because theoretically it should be infinite level. Okay. So to make a staircase to the sinusoid LOA form, but it depends on the applications.
Okay.
Because you don't want any filters, let's say.
Okay.
Then up to 13 level, we got a THD close to 5%. That is our findings.
Okay.
But if you go to the below 1% THD, even 87% is not sufficient.
Okay. Okay.
Okay. So
Okay.
it depends on the requirement and the advantages. So of course, more smoother are the sine wave is always better.
Okay.
Because the
Thank you,
moment
sir.
you put a filter, you got a capacitor that has a lifespan. That lifespan is much lesser than essentially the switches. So it is better to have a switches because you are not increasing the number of switches. Only you are changing the DC level voltage of the cascade multi-level inverter. 1:2:3. Sometimes 1:3:5. You have a different combination of voltage, and that you can do it by the boost converter. And you can generate the multiple level with the same kind of converter.
Okay.
So that is the beauty of it.
Okay.
Anyway, you write to me. I shall send you the papers.
Sir, thank you, sir. Thank you so much. Thank you.
Any other questions?
Hello, sir. Some question posted in chat box also.
Yes, please. Can you repeat the question? Sorry, I don't get you properly. Can coordinator repeat the questions?
Sir, the question was, what are the possible faults in microgrid system and fault diagnosis with microgrid system?
Achha, okay. Fault of the microgrid system is totally a different arena. Okay, so like islanding detections, as we have a power system fault, same can be repeated. Okay, and so mostly we got a different faulty conditions. Let's say we got a single phasing. That is a very common fault in case of the once we take the current from the microgrid. So that is something that the controller required to take a call whether we require to isolate the microgrid from the main grid or not. And of course, inside the microgrid there can be a different kind of fault as reported by the power system, and unfortunately, problem lies once you have a hybrid microgrid, then you got a AC, DC, both kind of fault. Detections of the DC fault is very much difficult to detect and suppress because DC doesn't have a natural zero. So those are a different entity. Mostly the people of the power system works on it. So those who are working on the power system mostly done with those kind of faults. My task was to, if the fault is been reported, then what action that controller should take. So, so we just see that if the single phasing has been occurred or something, then one of the line, then the 120 phase shifted become 120 phase shifted. It's a severe negative sequence component. Whether the active rectifier or the UPQC connected into the system can mitigate that problem or not. Because if it is overrating, it cannot mitigate it. So then it will shut down the grid. Okay. So detections, fault detections, fault removal is altogether total aspects of the microgrid. And it is more challenging than the normal grid. Because nowadays your distance protections in microgrid, distance protection doesn't work. It is a very small area.
Any other questions from participants? I think there are no more questions from the participants, sir. Thank you, sir, for delivering such a wonderful lecture to us. I hope our participants utilize this to their management benefits. Thank you once again for delivering lecture.
Thank you so much. And I have a couple of things to say to our participants.
Attending the session.
Yes, please.
Yeah. For giving your valuable time to us. Okay, so thank you.
I just want to say one thing before I leave. Thanks for your times, first of all. Second is that I am going to conduct a GAN course from 22nd to 26th with Professor Sheldon Williamson of Concordia University on electric vehicles. So registration is still open. It will be online as well as the webcast. So, but we have a limited seats for the online participants. If you're someone interested for the online, offline rather, classroom kind of mode. So please register. Thank you so much.
Sir, may I have a
Thank you.
link, please, sir?
Thank you.
Thank you, sir.
Sir,
Thank you
may I
very
have
much.
So I am leaving with your kind permission.
Yes, sir. Thank you, sir. Thank you very much.
Sir, may we know the link, sir?